Yorkshire. So does anybody have any kind of more general questions that they might like to pose to everybody? Somebody's talking. Okay, Michael's coming to the microphone. Can we have this microphone on the floor? Okay, I'll bring you this one. Shout.
This is a question to everybody. One use of noise in signal processing, which I think has not been alluded to directly, is the very nice theorem that if you put white noise through a linear filter, the output is, of course, the impulse response of the filter. It's widely used in practice to find out properties of the filter. I suppose what that means perceptually is that when we look at white noise, what we're actually seeing is, of course, not white, but it's the property of the filter, whole filtering property of the digital system. So my question is, since that use of noise to derive impulse responses has not been specifically mentioned, does anyone know of cases where that's proved useful? I think the only one that I can think of is work that's been done with stereo, where you just get people to look at dynamic visual noise, and then you impose a delay, interocular delay. Now, if that means that the temporally coincident signals arriving to binocular neurons would be completely uncorrelated, so you shouldn't see anything other than rivalry. But in fact, you see rotation in depth. And that's because, of course, it's going through a low-pass filter, which means that there is correlation between the signal in the right eye at time t and the signal in the other eye at t plus delta t. And Fowler and I use this to try to derive the temporal impulse response of the binocular system. So, my question is whether you know of other examples.
My understanding is that the classification image technique rests on the same foundation. You put in white noise and you get an idea of the impulse response of the filter.
Yeah, I mean, going by what Josh said, of course, there will be several examples, but I think Michael's question is interesting because if you have a target, as you do in the typical noise mix classification paradigm, and the system has even some small nonlinearity, that target will introduce distortions into what you estimate. So at that point, you don't get a picture of the front-end impulse response function. But what you can do is actually what Michael was describing. I think if you say you're running an experiment where you don't have the two alternatives for choice, but you just have a single interval, because there are some trials you got the target and some trials you don't. If you only analyze those trials where you didn't have a target, that's very much what you say. You're just showing noise to your observers. And of course you can find structure there. So and there are several examples in the noise image classification literature. So in those cases, presumably you are looking at your own filter, if you like, as you were saying. You're just getting noise, but when you analyze that noise, only when from different trials where the target was not presented, you can still see that there is structure. And it's an extreme example of that was an experiment that Sheens and Lane, I think, did, where they only presented noise all for the entire block, but they biased observers. They told them, look out for a letter A or something. And they did find that when they analyzed the noise, they could retrieve the template that observers were using, and there was some variability across observers. Some were seeing a bigger A, some smaller A. So that is probably as close as it gets to what you were referring to for the complete experiment. Yeah. They, instead of calling it impulse response function the way they call it suspicious perceptions, because the observer is suspicious that there is something in the noise.
My understanding, nobody's mentioned stochastic resonance yet, so my understanding is you have a threshold nonlinearity and you have noise, you can get stochastic resonance effects at either end of the distribution. I wondered, Keith, do you think stochastic resonance can come into your formalism for things? For contrast discrimination, either end?
I'll pass this to Keith in a second, but
sorry.
Stochastic resonance was featured in the thing I did in my article about Lou Doscher, 2009. It was all about stochastic resonance.
Oh, right. Okay.
It's very small, but it's not there. It is there.
Were you referring to the transducer model stuff, or the?
Well, I was just thinking of the model you have of the neural response functions at different contrasts. Now, presumably, if you've got multiplicative noise, then at the very low end, you haven't got much noise, so it wouldn't assist in detection. But at the higher end, then would the system, could the system saturate earlier, maybe, if you've got high levels of noise at one end? The reason I'm sort of asking about this is a suggestion that myself and others have made that increased levels of internal noise might be important in understanding conditions like autism, and how those effects would manifest themselves, and maybe stochastic resonance has a role to play in that. So
I don't really know. Are you talking about how, where if you add a bit of noise, it actually improves performance? Yeah. I don't think with the physiological model that I presented, I don't think adding noise like that would improve performance, but it's very difficult to intuit. I'd have to try it out.
Josh seems to.
Yeah, it's a classic. Kim Blackwell looked at it in a number of papers before our time, and he got very small effects, but not non-zero effects. The problem is designing the experiment appropriately so that the noise mask doesn't decrease uncertainty about spatial-temporal coordinates of the signal.
Okay.
Yeah. I mean, following up on that, when you if you look at the behavioral literature on stochastic resonance carefully, so that you read the papers, and the evidence is very limited. So there were some early reports with tactile stimulation, but essentially all those experiments, at least the ones that I found in literature, are flawed. There is no real demonstration of stochastic resonance there. So the literature, I think, is a little, as we were saying, there may be some effects that are small, and Ted Cohen was looking at it at Berkeley, but he thought that most of what was happening when you were adding the noise, if you saw an improvement, was that you were reducing uncertainty as to where the target was going to be. And that certainly explains the early tactile literature. So I would say it's one of those topics where experimentally it's not established enough to say much about it at this stage.
But as I understand it, it will happen if you have a hard threshold and
but then
noisy signal.
Yeah, one thing is to predict it, one thing is, of course, to demonstrate it. So I think the latter is still not settled.
Okay.
So,
I agree.
Just one comment while Alex comes up to the microphone. That I made a perhaps oblique comment at the end of my talk about a hard threshold, saying that our field may have reached a consensus about it. I didn't say what that consensus was, by the way. I'm curious though, do we have, amongst people with a strong opinion on the matter out there, and that maybe no one, how many think there might be a hard threshold? Raise your hands. For contrast. And how many think there might not be? Okay, so there might be a consensus among you five. Thank you. Alex.
So, maybe 20 and 30 years ago people thought the same thing, but there seems to be an emerging consensus here. This is not an infinitely complicated field. Possibly this historical, right? I mean, if we stand back in 20 years' time, Stanley, do you think you'll still be talking about this question, or is there going to be resolution at some point in my lifetime, maybe? And then what? So what's the impact of this? Oh, noise. What the issues to do with noise in the signal transduction process and the nonlinearities.
Oh, yes, I think there's going to be a resolution. I think what people here have been calling noise is going to be in the future called a mask. It's not noise. It's coming in and it's a complicated stimulus.
And then what? So then we have a standard.
Oh, we'll figure it out.
I'm not challenging, just saying, where next?
Well, my suggestion is to use noise that's more interesting so that you can actually figure out what the brain is trying to do with it. Right now, the noise being noisy, it's hard to really make use of it to figure out what the brain is doing. It's just another stimulus. What we're calling noise is another stimulus, but it's a very complicated stimulus. Progress has been made. Like many of the talks here, we're doing these averaging tasks where the noise was in something very simple, many fewer moving parts. So I think that's a better direction.
Pursuing thresholds, nonlinearities, and Dipper functions, there are several well-attested cases where you don't get a dip in the discrimination function. One example is the detection of dynamic visual noise on a dynamic visual noise pedestal. There's no dip in the energy threshold. Another's a case described by Josh, myself, and McEwen, which is far too complicated to talk about. And then there's one by Henning, I believe, with notched noise, which Josh certainly knows about. So, comments from the panel, please.
Yeah. Thank you. Peter mentioned the name Ted Cohn. So Ted was featured in that 2009 article. It was kind of a eulogy kind of a thing. So there's something called Birdsall's theorem, which is something by Birdsall that noise, if the external noise dominates the nonlinearities, then everything will be linearized, and so the Dipper function will go away. And so the Dipper function should go away. And the fact that it doesn't so many times means that people are doing something wrong, which we blame on uncertainty issues. So that was a very excellent issue, is why doesn't the Dipper function go away all the time in the presence of noise, if it's truly noise?
I really relate to Alex's question, because I think sometimes you sit here and you think, we're still discussing topics that were topical, say, 40 years ago. So can we see progress? And so, you were saying 20, 30 years ago, and I think there has been, it's limited, but the way I view it, for example, with the gate control model, is something that we understand much better now, definitely, than 30 years ago. And it has wide applications. So that is one line, perhaps, where I see that it's a very simple model, but it has a lot of potential. And there are other simple models out there that can do a lot, and that we understand much better. Also because there are new techniques now, like the classification imaging, in my opinion, which have helped clarify certain aspects, not everything. But this also brings me to another topic, which I think is a topic where we're making progress, but it's still controversial, which is the one of internal noise, which is extremely important. And one thing that I see that, in my opinion, is now polarizing, at least, that people are interested in this topic, is that there are different ways of measuring it, and these existed back 30 years ago, perhaps, although they were just starting like the double pass. And now is a discrepancy there. For the internal noise estimates that are derived from, say, that technique, the double pass, they're often very different and often inconsistent with those that are derived from other methods. And that's one specific area that I wanted to bring up, because from my measurements, what I've done, I essentially subscribe entirely to the late additive noise model, where it just scales with external noise. Because I don't see in my data anything that contradicts that, or very, very little. And I've heard you talk about other opinions, and for example, also when Josh was talking about the fact that in some conditions with very visible stimuli, you would expect internal noise to be very small. But with the double pass, I find huge internal noise, even with very visible stimuli. And there is the double pass, for those who are not familiar, is where you present the same stream of varying stimuli twice, and you check whether the observer gives you the same response on each trial. So if there is no internal variability in the observer, you expect those two response streams to be the same. But they differ, and they differ by a lot. Whatever you do, essentially, whatever you show, observers are not very consistent the second time around.
Thank you. Just one point of clarification. It depends what you're measuring. So if you're measuring thresholds, in high levels of external noise, then the internal noise is negligible. However, if your model is based, if what you're trying to model is the way that the observer will respond, it's all based on sample mean. The responses should be identical, not, it all depends on the specific sample of noise in the classical equivalent noise model. And so it depends on efficiency, right? So the two responses will be identical if you are 100% efficient, and if you're less than that, well, that's how it determines the correlation between responses with the same sample of noise. Oh, okay.
Within the detection regime, you would agree that it is, it can be modeled as a late additive source.
Thanks, Dan. The fact that you get a classification image means that it's determined by the sample of noise.
Yes, but there is also a certain difference. I mean, the reason, by the way, why I think this is relevant is that it does simplify your life a lot. I mean, if we can agree that internal noise can be modeled, that doesn't mean that it has to look that way in the brain, but it can be modeled as a late additive source. That's a huge help for the application of a variety of techniques. And the problem is that there doesn't seem to be really agreement on that. And many models like Dosher's model have noise in several places. And, yeah, I mean, at least within the detection regime, because you can still get a classification image even if internal noise is not late and additive. You will get something that is coupled with the stimulus. So
Dosher and Liu only are worried about thresholds. They don't worry about the individual sample of noise. So their model doesn't even address that problem.
well, they're modeled by fitting. What they do is they fit the data that you obtain from thresholds. So of course they don't do a trial-by-trial analysis, but they do fit it, and they do get other kinds of noise. The question is how much power do they actually have in the data, given that they have so many parameters. But in any case, I mean, it's just an open question. As I said, for example, I am entirely convinced that it can be done that way, which simplifies a lot of problems. But yeah, there is no complete agreement.
Do we have another question?
Yeah, just a short comment on internal noise. So if you take a completely deterministic observer that just learns and adjusts their strategy over time, then you get something that mimics internal noise. So all your double pass techniques will just imagine internal noise where it doesn't exist. So all you need is a latent variable model with random initialization that you can go on completely deterministically. So you may be measuring something that doesn't exist at all. So I was wondering what your thoughts on that were.
No, I mean, obviously, unless you assume stationarity, then there is very little you can say. because if you move into a non-stationary model...
But stationary makes some sense, you know that.
Well, it may not make sense for the first couple of blocks, but you know, with experienced observers that have collected thousands of trials, you can look at the first set and the second set and see whether your measurements change. We've actually done this with, for example, we measure noise, internal noise using double pass after a month. So we either did the double pass on the same block, or we repeated it a month later, and we get very similar results. There are some changes, they're not identical, so you're right that there is definitely something happening with non-stationarity, but they're not massive effects. Whereas here, the discrepancies that you're talking about when you measure internal noise using the double pass and METs are very, very large. I mean, typically for the double pass, your estimates of internal noise are in the order of 1 unit of external noise, which is huge. It's a very large source.
So Zach Lyman has non-stationarity in rats, like significant non-stationarity in rats that have been doing tens of thousands of trials. So you never get to stationarity.
Yeah, well, you will never get to full stationarity, I agree, but you do realize, I mean, if you start incorporating that, then yes, it becomes a problem of a completely different level of complexity. I mean, stationarity is assumed by almost all the techniques that are used in standard second physics. Well,
You can model that. You could model the non-stationarity as a form of internal noise. So I wonder if we should wrap things up there, because I think we've overrun by about 15 minutes and we're eating into the coffee break. But if we could thank all of the speakers and all of the participants, it's been very interesting.